For centuries, we've been taught a simple picture of the solar system. Mercury is closest to the Sun, Venus comes next, then Earth, then Mars. It seems obvious that each planet must have its own closest neighbor. Earth's closest planet should be Venus. Mars should be closest to Earth. Everything appears neat and logical when you look at those familiar textbook diagrams printed in school books and science magazines. But in 2019, scientists uncovered something deeply strange. According to the mathematics of planetary motion, Mercury is actually the closest planet to every other planet in the solar system, even Earth, even Neptune. At first glance, that sounds impossible. After all, Mercury orbits extremely close to the Sun, far away from most of the planets. How could it possibly be the closest neighbor to worlds billions of kilometers farther out? The answer begins with a simple shift in how we ask the question. For decades, people assumed the closest planet meant the planet that can come nearest at any given moment. By that definition, Venus occasionally swings closer to Earth than any other planet, but scientists began asking a different question. Instead of asking which planet gets closest at one specific moment, they asked, over long periods of time, which planet stays closest on average? When researchers ran the numbers across thousands of simulated years of orbital motion, the results surprised everyone. Mercury came out as the closest planet to every single planet in the solar system. At first, this seems like a strange mathematical trick, but it actually reveals something important about how planetary systems really work. The solar system is not a frozen diagram with planets sitting in perfect circles. Every planet is constantly moving. Mercury races around the Sun in just 88 days. Earth takes 1 full year. Mars takes nearly 2 years. Jupiter needs almost 12 years to complete a single orbit. And Neptune takes 160 to 5 years to go around the Sun once. Each planet travels at a different speed and along a different path. That means the distances between planets are constantly changing. Sometimes Earth and Venus are relatively close. At other times, they are on opposite sides of the Sun, separated by hundreds of millions of kilometers. The same shifting geometry happens with every pair of planets. Sometimes Mars is relatively near Earth, which is why space agencies often launch missions during specific launch windows when the distance between the two planets is smaller. But most of the time, Mars is extremely far away. These constantly changing positions make the solar system a dynamic, moving structure rather than a static map. So if you want to understand which planet is truly closest to another, you cannot just look at one moment in time. You have to track their positions continuously, measuring the distance between them every single day for years, even centuries, and then calculate the average distance across all those positions. When scientists did exactly this using detailed orbital simulations, they discovered something remarkable. Mercury's small, tight orbit keeps it relatively close to the center of the solar system. Because of that central position, it ends up being moderately close to every other planet for most of the time. Venus, Earth, and Mars orbit farther away, which means they often spend large portions of their orbits on the opposite side of the Sun from many other planets. The outer giants, Jupiter, Saturn, Uranus, and Neptune, are separated by enormous distances that stretch billions of kilometers. But Mercury stays near the middle of planetary traffic. Imagine the solar system like a set of racetracks around a stadium. Some runners are on huge outer tracks, while one runner circles tightly on the inner lane. That runner on the inner lane will statistically remain closer to all the others most of the time, simply because the path is shorter and more central. Mercury plays exactly that role in our solar system. Even though it rarely gets extremely close to other planets, it also rarely gets extremely far away compared with the outer worlds. Its distance stays somewhere in the middle, and over long periods of time that middle distance turns out to be smaller on average than the distances between the other planets themselves. The discovery emerged when researchers used advanced computer models to simulate planetary motion across long timescales. Instead of measuring a few distances here and there, they calculated millions of positional relationships between planets. Every possible alignment was accounted for as the planets orbited the Sun again and again. Computers tracked the location of each planet day after day, year after year, building a massive data set of distances. When the average distances were finally computed, the pattern became clear. Mercury consistently ranked as the closest neighbor for every planet. At first, many astronomers were skeptical. After all, textbooks have long stated that Venus is Earth's nearest planetary neighbor. That belief seemed obvious because Venus can approach Earth more closely than any other planet during certain alignments, but those alignments are rare and brief. Most of the time, Venus and Earth are separated by huge distances as their orbits carry them around the Sun. When the entire timeline of orbital motion is considered, Mercury spends more time closer to Earth than Venus does. The same pattern appears for Mars, Jupiter, and even the distant ice giants. The reason this feels counterintuitive is because human intuition focuses on extreme moments rather than averages. We tend to notice dramatic events, those rare times when planets appear unusually close in the night sky. Astronomers call these moments conjunctions or oppositions, and they can create spectacular views through telescopes. But these events are temporary. They might last days or weeks, while the rest of the orbital cycle spans months or years. When you average the entire timeline, those dramatic close encounters contribute very little to the overall calculation. Another important factor is the structure of the solar system itself. Most of the planets orbit within the same flat plane, known as the ecliptic. But their orbital radii are very different. Mercury's orbit is extremely compact. The planet never strays very far from the Sun, staying within about 58 million kilometers. Earth orbits at an average distance of about 150 million kilometers. Jupiter sits roughly 5 times farther away than Earth, and Neptune orbits nearly 30 times farther from the Sun than Earth does. When you visualize these enormous scales, it becomes easier to see why Mercury's inner orbit keeps it statistically closer to everyone else most of the time. But Mercury is not just mathematically interesting, it is also one of the most extreme worlds in the solar system. The planet has almost no atmosphere, which means there is nothing to trap heat or regulate temperature. During the day, Mercury's surface can reach temperatures hotter than 430 degrees Celsius. At night, when the Sun disappears below the horizon, temperatures can drop to minus 180 degrees Celsius. These dramatic swings make Mercury one of the harshest environments in the solar system. Its surface is heavily cratered, resembling Earth's moon, and many of those craters date back billions of years to the early era of planetary formation known as the Late Heavy Bombardment. Despite these extreme conditions, Mercury still holds clues about the history of our solar system. Scientists believe the planet may once have been larger before a massive collision stripped away much of its outer crust. Its unusually large metallic core suggests a violent past, possibly involving giant impacts during the chaotic early stages of planetary formation. Today, spacecraft such as NASA's Messenger mission and the ongoing Bepi-Colombo mission from the European Space Agency and Japan are helping scientists study Mercury in unprecedented detail. These missions are revealing new information about its magnetic field, its geology, and even the presence of water ice hidden in permanently shadowed craters near its poles. Yet the mathematical role Mercury plays in the solar system is perhaps just as fascinating as its physical characteristics. The discovery that Mercury is the closest planet to all others reminds scientists that even familiar systems can hide surprising patterns. Sometimes the assumptions we make about the universe are based on intuition rather than careful analysis. And when those assumptions are tested with precise data and long-term simulations, the results can challenge what we thought we knew. Understanding these orbital relationships is also important for studying distant planetary systems beyond our own. Astronomers have now discovered thousands of exoplanets orbiting other stars. Many of these systems are far more compact than our solar system, with multiple planets orbiting extremely close to their star. In such systems, gravitational interactions between planets can strongly influence their orbits. By studying how average distances behave in our solar system, scientists gain insights that help them model and understand these distant worlds. The same mathematical principles also influence how spacecraft travel between planets. When engineers plan missions to Mars, Jupiter, or beyond, they must carefully calculate the changing distances between planets and how those distances evolve over time. Spacecraft often use gravity assists, flying close to a planet to gain speed from its gravitational pull. Understanding which planets are statistically closer to each other can help optimize these complex interplanetary routes. From a broader perspective, Mercury's surprising role highlights a deeper truth about the universe. Space is not static. It is a constantly shifting choreography of motion and gravity. Planets move, stars orbit the centers of galaxies, and galaxies themselves drift through cosmic space over billions of years. The relationships between celestial objects are defined not just by where they are, but by how they move over time. When we zoom out even further, the lesson becomes even more profound. Our solar system is just one tiny system among hundreds of billions within the Milky Way galaxy. Each of those systems may contain planets with their own unique orbital patterns and hidden relationships. Some may have inner planets that act as central hubs like Mercury does in our system. Others may behave in completely different ways, shaped by the gravitational influence of massive planets or nearby stars. Mercury may appear to be a small, insignificant rock orbiting dangerously close to the Sun, but statistically it occupies a special place within our cosmic neighborhood. Over long periods of time, it quietly becomes the closest planetary neighbor to everyone else. This unexpected result reminds us that the universe often hides its most interesting truths behind simple questions. Sometimes all it takes is asking that question in a slightly different way to reveal a completely new perspective. And if something as basic as which planet is closest in our own solar system could remain misunderstood for so long, it raises an intriguing possibility. What other hidden patterns might still be waiting to be discovered in the vast and mysterious universe beyond?